To the next video on method of sections. And I was just looking at the situation I ran when I was an undergrad, and I still remember. So method of sections is a very powerful method to find the forces at specific members, right? Without having to start from one side of the truss all the way to reach the member you want. The method of sections will allow you to target a specific member, right? So if in the exam they didn't ask you to find all the forces in the members, but just this one, find the force in this member, the method of sections gives you a very powerful method to do so, right? So method of sections is a second method to solve for member forces, right? Why do we need another method, right? We had the method of joints, which once you get some practice with it, is quite nice, right? You will be able to see that it allows you to, in an efficient way and in an easy way, to get all the forces you need, right? The one of the main disadvantages is that you can only apply the joints with a maximum of 2 unknown truss members. Otherwise, you have to go to another joint, and then it starts becoming tedious, right? So you got joint to joint to solve member forces until all members are solved. Now, this is not very convenient if we are only interested in 1 or 2 member forces, right? We might have to solve many members that are not of interest to finally solve the members that are needed, right? So the member of sections will give us the ability to target the members of interest immediately. So we do not need to solve the entire truss. This is the key. This is the key element in the method of sections, right? It's very efficient. So learn this method well. It will save you time and energy, right? Now, the principles, or why does the method of sections work, is that if the entire truss is in equilibrium, right, then any and all subregions, you can read that as parts of the truss. If we break it into pieces, every piece will be in equilibrium, right? Every subregion or every piece of the truss. So if we cut a subregion out of the truss, right? So let's take a look at this truss, right? It must, if we break a piece, that piece has to be in equilibrium, right? So if we make a cut here, the 2 cuts must remain in equilibrium. So how does that work, right? How does that work? When we cut a truss, what happens, right? What happens with the forces we cut? So imagine we cut a truss into 2 parts along the dotted line, and then draw free body diagrams of each half, right? Now, it says here, right, as a suggestion, we can only cut through a maximum of 3 members of unknown force. Now, disregard this advice for now. Don't worry about this advice for now. I'll show you in a minute what's going on. So we cut, right? We cut the truss, and then what we discover are the forces that the members were hiding, right? That I like that part. So when you cut the truss, right, what you discovered were the forces that the members were hiding, right? That's great, because then right, the whole thing of the method is to, now that you discovered or kind of uncovered the forces, now we are going to target them with our equilibrium equations. How many equilibrium equations we have? 3, right? Well, you say, well, I have 2 that I could use in joints. Well, this is not a joint. We cut through the truss. We have a piece of truss there we can use, again, the 3 equations of equilibrium. So that's why the previous slide said that it's advisable to cut through 3 members, right, maximum, because then you have 3 equilibrium equations, and then you can find 3 unknowns, right? So keep that in mind. So we uncovered the forces, right? And now we have 2 rigid bodies. Now, from Newton's third law, right, the internal forces occur in equal and opposite pairs. So this force here, FGC, is exactly equal in magnitude to this FGC, but opposite in direction. And the same happens with this one. FBC, right, is exactly the same as this FBC. This should be CB, right? It's exactly the same but opposite in sense at force BC. And force GF, it's indeed, this is FG. It's exactly the same in magnitude as force GF, right here, right? So these are equal forces that happen at every half. So that's us cutting the forces, right? And then we can solve for any half we want, right? We can solve for any half we want. Suggestion: choose the half in which you have three unknowns, because then you have three equilibrium equations and you can actually use them, right? So if we choose the left hand side, right, we have three unknowns, right? The forces in the cut members, and then you have three equilibrium equations, right? Sum of forces in x equal to 0, sum of forces in y equal to 0, and sum of moments at a point equal to 0, right? We recover our moment equation when we do this. So what if we choose the right half, right? Let me just put here our sums. So what if we choose the right half? How many unknowns we have? So we have 1, 2, 3, 4, 5, and 6. 6 unknowns, but only 3 equilibrium equations. So we cannot solve for that half, right? So it's a good idea to choose the half in which you have equal number of equations than equal number of unknowns, right? Now, important, right? Important. When you cut the truss, right, you have to be aware of what type of forces you have in the member. Now, so take a look at this side of the slide first, right? We're working with that side of the slide. If I ask you, right, what force does element BC has? When you cut, right, you assumed this force. So does that case corresponds to tension or compression? Remember, we did a similar analysis for the method of joints, right? Now we have to do the same analysis for the method of sections. So when you cut through the members and you uncover the forces, right? When you are assuming forces such as these ones, right? Are these elements in tension or compression? Right? Now take a look at this side of the slide, right? So I cut through the member, right? And I found this force, right? FGC. Now, if I make it a small cut on the other side, right? On the other side of the member, a small cut, I find a force that shows me that indeed this is the force in the member, right? So this force is stretching my member. It's acting in the member. So this element is in tension, right? So I can say that the way that these arrows are drawn here in this drawing, these elements, all of these elements are in what? Tension or compression? Tension, right? All of these elements are in tension, right? So, and then we know that because the forces are right in the member, right? It's not in the, like they were in the nodes as before, right? So it's important that you realize what sort of forces you get when you cut your truss, right? When you cut your truss. So I think in the previous slide, I am showing compression, right? So what happens in compression? So make a small cut and you find the other force. So this element is in compression, right? So things to consider, right? Things to consider. When choosing the cut line, do not cut more members than you have equilibrium equations, right? Usually 3. We will see in a minute that you can actually cut sometimes through more than 3 members, right? But certain conditions have to be met, right? Have to be met. So choose only one of the 2 sections to analyze. Forget about the other one. The other is in equilibrium. You don't have to worry about the other section, right? Just choose one. Choose the more convenient for you to solve, right? Now, when setting up the equilibrium equations, try to involve as few of the unknowns as possible in each equation, right? Because the equations are solved simultaneously, right? So just it's good to have one equation, one unknown, right? Don't mix one equation, three unknowns, because then you will need another equation, right? Just try to be as have one equation, one unknown, so it can lead to a quick solution. Now, coming back to this point, right? That we advise our students sometimes to only cut to three members because you have three equilibrium equations. But in fact, you can, in certain situations, you can cut through more than three members, right? But certain conditions need to be met, right? For example, to cut through more than three members, the trick is to obtain or to apply your moment equation, right? In a smart way. For example, a trick is to sum moments about a point which will eliminate some of the unknowns you have, right? So if you have more than three, if you choose your point well to calculate moments, if you choose that point well, then you can eliminate some of the unknowns, right? That's the trick, right? That's the trick. We have seen that before, in which we choose our moment, our point in which we calculate moments as the point that has one or two forces just crossing down. We can eliminate them, right? Now, the nice thing is that this point does not need to be in the section you are analyzing. It can be outside, right? That's a nice way of calculating moments, right? So I'll show you an example in a minute. So this is the same truss that we solved before, and now we are asked to find the forces in members GH, right, this one, and CH, these two members, right? We are not asked about the other members, right? It's only these two, and then we have to tell if it's in tension or compression, right? Compression or tension. So this is a very nice example about the method of sections, right? So in the method of sections, previously we solved this truss with the method of joints. So we have a good idea of what the forces are, right? Now, the first step in the method of sections is the same as in the method of joints, to calculate the reactions, right? So calculate the reactions is the first step. So first step, calculate reactions. Right? So we calculate the reactions and we find the same numbers as before. At point A and point E, we got the same reactions as before. Right? Remember, we are looking for these forces, GH and CH. These are 22.5 compression and 12.4 tension. Right? So we have our reactions, and it's a time to cut. Do we cut through this line? We are cutting through 1, 2, and 3 members. So it's a perfect cut because it gives us 3 unknowns, at least at that part. We have to make sure that we don't have any other unknowns, right? Now, if we cut over there, right, which half would you choose, right? Well, you may actually choose the one that has the least amount of forces, right? The least amount of forces. For example, you choose, let's say, the left-hand side. Now, before we decide that, nobody told us what sort of forces we have in the cut. So it's up to us to analyze it, to assume the sense. So in this part, right, a preference of mine is to always assume that the forces are sticking out from the members, right? Just a personal preference, right? And then once we apply the method and we obtain our forces, if some of them are negative, that means that the forces were reversed, actually, right? Now, let's decide, and these forces, right? So which ones are tension and compression, right? Before I forget. So all these forces will be tension, right? It's very unlikely all of them are tension because in order to equilibrate the other half, some of them have to be in compression. But anyway, we will discover that when we solve for these forces. But at this point, all these forces are assumed to be in tension. The moment has arrived and we have to choose a half, right? So let's say we choose the smallest half, right? And we have 3 unknowns. and 3 equations of equilibrium, right? So we apply our equations, right? Sum of force in x, sum of force in y, sum of moments equal to 0, sum of force in y equal to 0, right? So I see an 8.5 force over here, so 8.5 positive. I see a negative component of FCH, so FCH sine of 45 negative, and there is no more forces, so equal to 0. So one equation, one unknown, I can find FCH directly, 12.4. And then it's positive, so that means that the sense we assume for this force is actually correct, right? So it's going to be a tension force. And we calculate moments about H, and we choose H because it gets rid of many forces at once, right? So some force at H equal to 0, right? Counterclockwise is positive. I see a force of reaction, right? Having counterclockwise moment about H, 8.75 times 3, positive. And then I see a force, right, FCD, doing clockwise moment about H at 3 meters moment arm, so minus 3 times FCD equal to 0. One equation, one unknown, I can find FCD as 8.75, positive. So the sign is correct, this force is positive in tension, right, in tension. And then it's time to find FGH. We can do that with sum of force in x equal to 0, so we have negative FGH, right, this one, minus 5, minus FCH sine of 40 or cosine of 45, right, either way, minus FCD equal to 0. I know FCH, so this guy I know, FCD I know as well. FGH is minus 22.52, which means that, right, the sign of this force is wrong, and the sign and the force should go into the member, meaning that it is a compressive, right, 22.52 compression, right, which happens to be the force, right, the same force that we found in the method of joints, right, in the method of joints. The last example, right, illustrates a cut with 4 members, right? So you are given a very what seemingly a seemingly complex truss, right? The reactions, thankfully, they have been already obtained, right? They have been already obtained, and then you are told that we have to find the axial force, the forces in the member, right? In members AB, AD, here, VF, and FG, right? The reaction forces have been calculated already, thankfully, right? So we have to find the forces in the red members, One may feel tempted to cut through AA, right? Because that cut will actually uncover the forces in all the requested members, right? Now, if we cut through AA, right? If we cut through AA, I will leave it as an exercise to you, right? It won't work, right? It won't work because you will have really many unknowns in just your 3 equations of equilibrium, right? So you won't be able to solve. But we can use cut BB, right, to get close to some of the forces in the cut, right? So if we do the cut at BB, right, we can find the force in AB, and then from there you can continue your cut AA later, right? And then it will work, right? But cut BB cuts through 1, 2, 3, and 4 members, right? 4 members. So we shouldn't be able to do it all, but we are going to do it yet, right? Still. So if we choose cut BB, and then you may be wondering, how do you know that cut AA doesn't work? Well, I leave it to you at home to try cut AA. It shouldn't work, right? It comes with experience, and we have to try different cuts, right? It's just not as direct as I mean, we have to put a little bit of work on that. When we cut through BB, right, as I told you, right, my preference is that we assume that all the unknown forces are in tension. So all my forces are sticking out. You may see that, right? You may see that. I have 4 unknowns, right? And then if I take moments at G, right? But then you say, well, if you are choosing that cut and you are choosing the right-hand side, point G is outside the half you chose, but it doesn't matter. We can sum moments at points outside the cut, right? The point doesn't have to be at the cut. So if we take moments about point G, right? So I'm here now, right, on the corner, right, in the left hand corner. If we take moments about G, we can actually eliminate a bunch of forces, right? You see the forces that got eliminated? Let me just go back. Did you see the forces that got eliminated? I can eliminate this guy, I can eliminate this guy, and I can eliminate this guy. So I have only force FAB and the reaction to play with. So 6 times FAB, right, is counterclockwise moment with point G, plus 8.33 times 8 meters, right, counterclockwise moment as well. And I find FAB as minus 11.11 kilonewtons, right? This means that the right side sign of this force is actually into the member in compression, right? So 11.11 in compression. Now we can go back to cut AA, and then I can assure you it will work, right? And then you can find these forces. So I will leave this to you as an exercise, right? And the takeaway for this section is that yes, sometimes you can cut through more than 3 members, as long as you have a nice moment equation that allows you to eliminate some of the variables, right? Some of the variables. And that is the method of sections. In the next topic, right, we will deal with something called internal forces, right? The rigid body, we saw what happens when it's acted by external loads. We calculate the reactions. And now it's time to go into the rigid body and see what sort of internal forces it develops. Yeah, they cancel each other out because they are equal in opposite sense. They are equal but have different sense from particle to particle. But nobody has quantified them before, right? Now we're going to quantify them in the next topic, which is very fittingly named internal forces. Well, thank you very much, and see you on the next video.